Okay. So you've got a rise that's the same as this, okay? Even though the function has a little bit different derivative at this point, usually, okay, it might be the same, but you're going to use the rise here because everything's being evaluated at this point, right? Implicitly, fx and fy are evaluated at xy, not at x plus dx or y plus dy, or f plus dx, y plus dy, right? At this point, not any of these. So based on the values at this point, based on the slopes at this point, we have these triangles. We use a triangle similar to this one over here, knowing that it's going to be a little bit different. And that little bit of difference is going to be real important when we talk about Green's theorem, which you're going to love. Okay? We're not going to talk about that now, but the same picture is going to help us a lot. Okay? Which is why I cut that little thing out of wood and told you to live with it. You know, keep it under your pillow when you sleep at night, you know, have it on the table in front of you when you eat. Okay, so, get it? Okay? So, what you get here is, well, the value here is f of xy. Okay? Now, this is getting all cluttered up. And, of course, you're going to do a similar triangle here. This triangle will be similar to this one, right? Obviously, it needs to be. If this is similar to this, then this has to be similar to this if it ends up at the same point, right? Okay? So what we have then is f of x plus dx, y plus dy. Okay? Now that's going to be this value, right?
Is that the very back of the?
That's this segment here, you'll see in a minute. Okay? This down here is the point x plus dx, y plus dy. So we're just isolating the values here because that's really what the differential is talking about.
Okay.
Okay? Now you do have the original value of f of xy, right? So here's the value f of xy. It doesn't occur at this point, okay? But you have that for reference. The way I've drawn it, it's a little bit lower, right? And you have the rise here, okay? Which maybe corresponds to your fx dx. And then you have another rise corresponding to fy dy. Okay? Then you have the discrepancy between this, which is here, and this, which is up here, right? So I can draw this. This is your df. Okay? And I didn't, it's, that's actually your f plus df. Okay? Let me fix it. I think I'd be getting good at fixing these things, as many mistakes as I make. Okay? Here's your df. Okay? Your delta f, so here's your fx dx, I'm just going to project that across. Here's your delta f. That's the actual change in the value of the function. Because this is f at this point, right? This is your approximation, okay? Approximation to what? To the difference in the value of the function at this point relative to this point, okay? The change in the function as you move from here to here. So here's your actual change in f from xy to x plus dx y plus dy. Okay? And over here is your approximate change in same thing f from xy to x. I'm not going to write all that out. Based on fx and xy evaluated at the point xy. Because remember, these slopes here are your partial derivatives evaluated at this point. Okay? So that's the differential, the meaning of the differential. Also, note that these 4 lines here describe the tangent plane, right? Which you calculated for homework by doing a vector in this direction, a vector in this direction. Cross product, get the normal, you got the point, you got the tangent plane. Okay? So instead of, if you're wanting just to look at values of the function in the vicinity of this point, and you don't want to be too awful precise, you use the tangent plane. It's easier to evaluate. It's linear. Okay?
Why is it easier to evaluate?
It's linear. It's an easier expression. What if this function has 48 terms or factors that all depend on x and y, right? Which do you want to evaluate? All that or the simple expression for the tangent plane?
Well, you still have to get the tangent plane.
Huh? Well, yeah, but once you have it now, you can do all kinds of things with it and evaluate it lots of places. It doesn't take long to get the tangent plane. Once you got the partial derivatives, you just about write it down. Okay? I mean, you know, partial derivatives of the point, you do the cross product, and it's all numbers. Okay? So, plus for theoretical reasons, it's much easier to use tangent plane approximations for a lot of things, okay? Another thing is the differential is used, for example, to calculate the error you get if you evaluate the acceleration of a ball going down the ramp with a 2% uncertainty in your observation of the time and a 1% uncertainty in your measurement of the distance. Okay? And we're going to do that. Okay? And this is exactly what you want to use to do that and to understand why the errors you get are what they are. For example, you know, the acceleration depends on the square of the time, but is first power of the distance, okay? So you write the function that you get from the time and distance, which you can easily write down, okay? And you do the differential. And then you understand the error. Make sense? Well, maybe not because we haven't done it, but this is another use of the differential or the tangent plane, because they really are the same thing. Just different pictures of the same phenomenon.